Okay. Once again, we're going to take a look at applications of exponential functions. And we're going to keep it simple. Most of the questions will try to give you some clue to the values for a, b, x, n, as well as potentially the value of y or f of x. It is up to you to read and recognize what the initial value might be, what the growth or decay rate, in other words, the base for the exponent might be, what the power is in terms of time, and if the time has to be modified by a kind of a periodic or cycle factor. Okay. Not only that, one thing I'd like you to watch out for is um, the time frame. The x value, or the time that we use, the growth rate or decay, and the periodic factor that we apply, so b, x, and n, they all have to agree. They all have to have the same time frame. And that, I think, shouldn't be new to you. Like, you would have to do a kind of unit conversion if, the question asks for hours, but the question gives you minutes. So you'd have to make a conversion. Or if the question asks for kilometers and the question gives you meters, those type of questions. It's the same idea. As you work through it, and you'll be better and better at it, the growth, the base, the rate, the time that passes, and what we divide the time with all have to be the same time frame. Okay? So our goal will be to read and be able to identify. I want to go through the first maybe two, three questions together. And from there, hoping that you build some confidence, you can try maybe four, number six, number seven. If you have your sheet in front of you, you'll know. There are two questions that I don't want you to do right now because they have very little to do with application of exponential. Number five is just another kind of puzzle to keep your brain, I guess, sharp for exponent laws. Sorry. And number eight is just an example of when you get raw data, how we can still identify it as an exponential function and pull out an equation from it. We may not have time for that today, but we'll see. Okay, so let's get started. Here are some examples of exponential functions that you might see in words. So going back to, I think, what, 3.2, 3.3? That's right, 3.2. If a question says it doubles every hour, this statement gives you two very important pieces of information. The doubling portion will tell you how quickly we're growing. So my base value is going to be 2. And if it grows by 2, or if it doubles every 2 hours, that's not how much time has passed in total. That's actually how much we have to divide the total time by so that we know how many times we're actually multiplying that base. So for something like this, my f of x could be, I don't know what my starting value is, but my base would be x divided by 2. And you know what? From now on, because we're typically talking about time, I'm going to use t instead of x. Okay? So this is where we're going, trying to identify what we read and matching it with the equation. Any questions or concerns about that, or any confusions before we continue? You might want to see some more examples before you ask. So let me do this next one, and it might answer your question. Half-life of 25 years. So we've looked at a bunch of radioactive decay, carbon dating, nuclear power plant, those kind of examples. And you'll see there's another example in the sheet I gave you that mixes in medicine, like drugs, like acetaminophen or Tylenol, and certain things. To me, stuff like that is really exciting because, well, that was my university study. I studied toxicology, which is a study of toxins and things that are harmful to a human's body. And so even medicine, too much of anything good can also be bad, right? Like if you take too much Tylenol, it's actually bad for you. So I'm going to mix in some of this stuff to open your eyes to the wide world of functions. Half-life, again, automatically tells me that the base that I'm going to be multiplying with again and again is 1 over 2. half-life of 25 years automatically tells me that whatever my exponent is must be divided by 25 to make sense of the question. So again, if this was a question that was given to me, I don't know how much radioactive material that I'm starting with, but my base is half. Oh shit, I told you, I said that I was gonna use T, but I didn't. Oh no, do I have to erase the entire thing? Okay. So function based on time, this would be some a value multiplied by half, and the time that is passed is divided by 25 years. Now, of course, this is based on based on years. This is 25 years, so the time that we have to put in must also be in years. They have to agree. Okay. Oh my gosh, are you serious? I can't even erase my email? Roundabout way. Okay, let's do it. Um, any questions so far? All right, let's keep going then. Sometimes the question will give you the base in terms of a percentage. If it grows at a rate of 2%, that is 2% or 0.02 on top of the original 100%. And of course, 100% written in decimals would be 1.00. So the growth rate is actually going to be 100 and 2%, 1.02. And I think that makes sense if you talk about something like taxes. I hope you know, right? People don't know. What is the tax in Toronto right now? Someone, please?
Um, Income tax or like purchase income?
No, no, sales tax. Like you go out buy something. What's the tax rate?
13,
I'm
13,
hoping I can't quite hear you, but I'm going to assume that you said 13%. That's right.
13%.
Wow, thank you. Thank you. I appreciate that, I think. So when you're calculating tax, let's say you buy something for $100, right? You have to add on the extra 13%. Well, 1.00, 100%, if you convert it into numbers, is 1.00. If you're not quite sure where that's coming from, remember, here's a little detour. 100%, in other words, 100%, in other words, 100 per cent. Ooh, I missed the point. And what is cent? Like, in French, what is cent? Or cent?
100. That's derived from Latin.
100, 100. Yeah, it's going to be one. Okay. Percent is the same as saying per hour, is the same as, per kilometer or whatever. It's
Per 100.
per 100. So 100% is 100 per 100. It equals to 1.0. All right. Oh, geez, I keep on doing that. Sorry. Okay. So going back to this, tax is going to be 13%, and we have to add it on to the original 100%. So $100 plus what is 13% of $100? Well, of is another way of saying of in mathematics is multiplication. So that 100 added to 0.13 times 100, which is 13. You have to pay the store $113. Is there a way to not do so many calculations, do it in one big go? Yeah. You take the $100, you're multiplying by 113%. So I'm growing this by an extra 13%, which is another way of saying 1.13, and you get $113, just like before. So when you're given a rate of growth, know that it is a growth on top of 100%. And so if I were to have something like this in my math my word question, it would be f of some time. Oh, sorry, this is also per annum, which is per 1 year. So the function would be some starting value is going to be growing by 1 plus the rate, which is 1 plus 0.02, right? 1 plus the rate to the power of the time divided by 1 year. And of course, the time would be in years. Otherwise, we'd have to fix it. This would turn into 1 plus 0.02 over to the power of t. Okay. I don't think we got a chance to do some of the appreciation depreciation questions when we were going through chapter 3.2 because that lesson was jam-packed. But if I say it appreciates by 10% a year, again, that's the exact same thing as growing at a rate of 10%. So without going too much into detail, your equation would be 1 plus the 10% to the power of t. It's 1 plus the rate per year. But divided by 1, you don't have to write that, so you won't really see it. And of course, the last thing I want to do is if money can go up, it can definitely go down as well. Appreciation is an addition of the rate. So using your logic, what would you expect a depreciation to be as in terms of a formula? F of t, a, something is happening to the power of t every 1 year. What would you expect a depreciation to look like? Use logic here. If appreciation by 10% means I am adding, yeah, thank you, Noah. A depreciation by 10% means I'm subtracting that amount from the original 100%. So this is 100% subtracted by the rate. 100%, it would be 1 minus r. The reason why I want to point that out is sometimes when we're depreciating, some people are so prone because they're tunnel visioning. Sometimes they just write the 0.10 and think you're supposed to multiply by 0.10 all the time. That's not true. 1 minus 0.1, the fraction, the bracket is supposed to be 0.9 to the power of t. Okay, so please be careful of that. In my special Tylenol degradation or metabolism question that we're going to do together, you will see an example of a depreciation happening, so pay attention. At this point, I want to try some questions with you. Are there any comments or inquiries before we get started? Okay. Well, if you haven't noticed, we're basically starting our test review. This is part of it. And questions like this, I think you'll be able to develop some confidence in doing word questions after today because they're very similar and just have to know how to identify the numbers so that you can spend maybe the weekend just going through things like transformation and chapter one because chapter one's pretty heavy. I'm going to clear this. Uh, 3.6, yes, 3.6 is the last bit, but it's basically a redo of chapter 3.2. We're going to look at a bunch of word questions together. All right. So I hope you have the sheet in front of you. I'm going to go ahead and clear this and we'll do some questions together. I'm going to start with number one. And number one says this. I'm going to read this very quickly. Oh, of course. Of course I closed the window before I did that. Give me a second. Of course. My class this one, chapter 3.6. Oh, by the way, answer key is already up, and some people already caught some mistakes, so it should be pretty accurate now. Okay, I'm going to quickly share the handout with you to draw your attention to the beginning. So when you are doing word questions and you notice that it's going to be an exponential, what I like you to do is try to identify as many of these values as possible so that we can plug it into the equation. The first, easiest one is to identify if they give you a starting value. Next, see if they give you some information about a growth or decay, like is it a doubling, is it a tripling, is it a halving, is it a growth of 2%, is it a growth of 20%, is it a decay of 50%, whatever. See if you can find some information about what we multiply. And lastly, pay special attention to the time frames because you need to make sure everything agrees with each other. Right, let's start. Bacteria is grown in an incubator for the study of a new cold medicine. This coming straight out of my life when I decided I didn't want to go into research. I spent an entire summer raising and then killing and harvesting the organs of 60 lab rats. And when you spend an entire summer growing and killing rats, you decide you don't want to do research anymore. Okay? And then I moved on to bacteria, and I didn't want to do bacteria either. But here it is. If you use a sample of 1,000 bacteria to start, the population is known to triple every hour. It says to sketch a graph, and then tell me what transformations are current for the parent function of 3x. And then it gets you to calculate something. What's the population after 1 day? To do all of that, we're going to have to identify the A, K, so the A, the B, and all that stuff. Okay? So starting off, right away, I see 1,000. That's going to be my initial. So from here on out, I'm going to use the letter A as my initial value. The population is known to triple, so my base is going to be 3, and it happens every hour. My n value is going to be a 1. All right? And that's all we really have for now. Sketch a graph. What transformations have occurred when the parent function is 3 of x? Well, that's true because that's where we got it here. Let me turn this back into a whiteboard. So I have A value is 1,000. My B value is a 3. My n is just 1. Let's find the equation. So how about instead of f, I do population of bacteria over time is going to be 1,000, 3 to the power of x over 1. And because over 1 is redundant, let's not write that. What transformations have occurred from the parent function of 3x? A brave soul, take a shot. Right on. Thank you, Ian. It is a vertical stretch by factor of 1,000. Please use the word factor, because if you don't use the word factor, it means it's not a multiplication. Okay, a factor is what indicates that you're multiplying the y values. So there it is. Great. It says to sketch it, so I'm going to be really rough here. It's asking you to sketch. My parent function is going to be, let's see, if x equals 0, the y value is a 3. So that's a 3 right there. If my x value, oh, sorry. Yeah, so if my x value is a 1, my y value would have been, what am I doing? This is 0, 1. If my x value is a 1, my y value is 3. Okay, that would be 1, 3. So it will look something like this. This is 3x. A vertical stretch of 1,000 means, oh gosh, my y-intercept is going to be 0, 1,000 because everything's multiplied by 3. And so it's going to look something like whoosh. It's going to be really thin and really high, really stretched vertically compared to my parent function. Okay, so it's just a quick sketch. If you don't like what I just did and you wanted me to do it by scale, I'll try. I'll try a scale to help you out a little bit. This is 0, 1, 1, 3, 2, 9. This is my parent function. That's 3x. And then I'll use black. If I do a vertical stretch, my y-intercept is there. So this is basically stretched up so high that even before I get to the x positive side of the Cartesian coordinate, I'm already up here. It's going to be huge. Okay? So let's use it. My bacteria, so this is part B, is 1,000 times 3t. It's a t, sorry. What is the population when I have my time is 1 day? I have a problem. What is my problem?
Hours.
Yes. This base it triples every hour. So my time has to agree with my multiplication factor, my growth factor. So you will turn this into hours. And so what you're putting into the equation is 24, not 1. Now is a good time for you to test your calculator to make sure you know how to use exponents. All right, some people, you'd be surprised, they come to the test day and they're like, what button do I press? Well, I'm not going to tell you. You should have figured that out during your practice, not on the day of the test. So figure it out. Whether it's y to the power of x button that you have, whether it's a hat button that you have, whatever the case may be. Someone reach, let me know what the answer is while I pull up my answer key. Whoa, that was fast. Ian's got 2.82. Yes, so your calculator will not be able to handle how big this number is. So it will use something called scientific notation. It's going to look something like this. Some of you, depending on what your calculator is, you'll have 2.82 blah, 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 and then you'll have a little tiny 14 on top. This is the calculator's way of saying there is a 10 to the power of 14 multiplying to the answer you get. Okay? So that's how you translate it. Please make sure you know what your calculator is saying. The calculator is only as effective as the person who uses it. That's a lot of bacteria. Okay. Any questions? I'm going to move on to number 2 otherwise. Going once, going twice. All right, let's do it. Number 2. Number 2 states, let me read this again. I'm going to share screen. I'll share this again. All right. Number 2, Mr. Kim needs to make money for his family. A typical return rate of the S&P 500, C, investing. By the way, if you're into investing and you know what's happening right now, the stock market is dying because we're trying to recover from the COVID situation. There's a lot of stuff happening there, but you would only want to know if you're interested. So, the S&P 500, something you can invest in, is returns a 10% per year on a typical average year. I don't know about this year, but it gives you 10%. So this right away is your growth rate. Okay? If he invests $5,000, so that's going to be my starting value, and I don't touch it for 25 years, that's time, how much would that grow to? I'm missing something. I'm missing my N. Oh, 10% a year. So you multiply that 10% where n equals 1. Let's write it all down. Let's write it all down on our whiteboard. Okay, my A value, I start with $5,000. My B value in this case is a rate, so it's going to be 1 plus my rate, which is 1.10%. This happens every year, and my time is 25. Oh, Lucas got it. Yeah, it also might say e plus e to the power of, or e plus. Yeah. Okay. E as an exponent, so 10 to the exponent of 14. So what is my final amount? So how about I do A for amount based on time? We've got 5,000 to start. Oh, how about I do the, so here. This is what we had before, right? So we're going to match it. The total amount when time is 25 years is 5,000. My base is 1.10. My time is 25, and it happens every 1 year. So just you don't have to write the divided by 1. Plug that into the calculator. Do. Someone other than Ian, just to show that, there's more than one person that knows how to work their calculator. But it's true. You'd be surprised, people. There are people who just refuse to touch their calculator until the day of the test. I don't know why. 54,173.53. Because we're dealing with money, you're going to have to give me all the way to the cent. Otherwise, people will think that they're gypping you. Okay? And that's important. Let me tell you how important it is. You know when people come together and talk about like a hostile takeover or a not so hostile, like when one company wants to buy the shares of another company and sort of like merge together and they want to talk about how much do I owe you if I want to sell, they argue to the penny. They argue to the penny. It's like, here, let me give you $100 per share. It's like, no, give me $100.01. It's like, no. Let's give you that. Why? Because this share is multiplied by a much larger number, right? Million, billion. Yeah, like the company could have a billion shares. So a billion times $100.01, that 1 cent equals $10 million. So each penny is very, very important. When you're writing money, please give me the cents as well. Super important. Okay. Is that it? I think that's it. We finished number 2. Now here comes number 3. Please be careful. And this is one of my prize questions. I really like this one simply because, it alludes back to my young Thundercat days. All right. Number 3. The active medical ingredient in the cold medicine Tylenol is called acetaminophen. A single pill of extra strength Tylenol contains 500 milligrams of acetaminophen, and the body will metabolize and digest at the rate of 25%. Does that indicate a growth or does that indicate a decay? I'm hoping you recognize that this is not just the base value of 0.25, but that my base is going to be 1 subtracted by the decay value. It's a 1 minus r. Per hour tells me it's this. Okay? And here it is. An adult takes 2 pills of 500 at a certain time. So my starting value is going to be 1,000 milligrams of this drug. This is what I mean by pulling information out. Let's do this together, okay? Where's my whiteboard? Okay, my starting value for number 3 is 1,000 milligrams. My growth rate is 1 minus r, which is 1 minus 25%. So I am multiplying by 75% every single time. How many times or how often? Every year. Every hour. Sorry. How much time has passed before we check its dose? The question asks, how much is left in your body after 6 hours? So again, here is our typical template exponential function. I start with 1000. I am multiplying by 75%. So 75% is left over. 6 hours has passed, and I have to multiply every 1 hour. So 6 over 1, that's 6. How much is left in the body? It's always 25% of how much you take. Interestingly enough, there is a decay rate that is in your body. And you'll see a little later how that doesn't always hold true. In part C, there's a question I ask you, but for now it's 25% of whatever is left in your body gets decomposed. Ian is asking, oh, Noah, you got it. Ian is asking, why is it 1 minus 0.25? So basically, if it's a growth rate, we are taking your original 100% and we're adding a certain rate to it. If it's a decay or a metabolism or a detox or whatever you want to call it, if it's a removal, yes. So whatever original you have, the rate is subtracting from it. So if it's a growth, we're adding to the 100% and we want to get bigger. If it's decay, yes, exactly. That's why we are starting with 1000 milligrams and not 500 milligrams. So my original is 1000 milligrams. The original 100% being the 2 pills. Right? This is equivalent to 1 pill times 2. So how much is in your body? 1000 milligrams is in your body. That's what we're going to start with. Does that work? Does that make sense? um, okay, everyone else, work on that, please. I'm going to try to explain this portion a little bit better. Okay? This is you. All right? Oh no, remember, 100% is 100%. It's the total. 100% in this case is 1000 milligrams. If I only took one pill, 100%, so the maximum you have, the amount that you start with would be 500 milligrams. Remember, percent is an idea, right? So how much is the max, how much is the total that you have right now? 1000 milligrams. How much is the entire thing you have now? It's 100%, right? Okay, I realized I was going in the totally wrong direction by drawing this and talking about percents. I get the question now. My sense to me is if you do 100%, you'd be nothing. Oh, that's not true. That's not true. And this is what's interesting about money as well, Lucas. Take a look. Let's pretend you got $1,000 and then you multiply by this. You're left with 750. The next hour, let's say you got 750 and you lose 25% of that again. Guess how much you got? Let me use my calculator. 750 times 175. Oops. I'm left with $562.50. Yeah. So that's why it's not like I'm taking away 25% of the original. I'm taking away 25% of whatever I have left at that moment. Yes, if you're subtracting, but that's not the case here. I'm calculating, I'm subtracting to calculate how much that actually remains. 75% of whatever's in my body remains in my body. It's not that I'm taking away 25% every single time. It's not a fixed amount that I'm taking away. Yes. So I'm using this on the side to figure out what I need to put in right here. Okay, and I think Noah got it. When you calculate this, you get about 177.9 something. So you have about 178 milligrams left in your body. 0.97, correct. Right? So here's the next part. Part B asks, all right, if you want to actually feel the effect of the medicine, in other words, not feel sick, then you need at least 200 milligrams in your body. Clearly, this isn't 200, so you're going to start to feel sick by the 6th hour. Exactly when do you feel sort of ill again? So my question is, how much time has to pass for us to have 200 milligrams left? Okay, so you're going to have to do a little bit of guess and check. So if I give you a question like this and you have to figure out the x value, I didn't teach you about logarithms, so the best you can do right now is guess and check. So we can try 1000, 0.75. How about we try 5 hours? Can someone work with that through me? Work that for me? It should be 200 something. Someone other than the 3 people that have been working the calculator for me. Thanks, Emily. 237.5. You're right. This is still in effect. Like you still feel good, right? You don't feel sick. So let's take it a notch higher. Maybe an extra 30 minutes passed. So that would be 5 hours and 30 minutes, 5.5. How much drugs is still left in your body? Somebody else. Show me you're working your calculator. Going once, going twice. All right, for the sake of time, I'll just keep going. It's about 205.51 something, so it's really close. So you can say at about 5 hours and 30 minutes, you start to feel symptoms. Anyone know from their experience with Tylenol? What do they recommend your dose to be? How often do you take your next dose? Yeah, there you go, Harriet. 4 to 6 hours. Why is it 4 to 6? Because everyone's a little bit different. Some people will metabolize a lot faster just because of how strong their liver might be. Some might metabolize slower. But they're saying you won't need the next dose sooner than 4 hours for sure. You still should be feeling the effects of the Tylenol. There's also another reason for that. Your liver is limited in the ability to metabolize Tylenol, and if you take it for too long, your liver actually starts to suffer and starts to actually be damaged or might hurt itself. And that's why in the bottle, if you look at it, because your liver has a limited amount of resources to break it down, it'll say don't take it more than 7 days. If you're taking it for more than 7 days and you need it, you're not sick because of a cold, it could be because of a bigger issue. So go see a doctor. That's why they say stop taking it and go see your physician. Interesting, huh? Little things you never knew. That had math in it. What? Okay, part C. It says if you were to graph it, what does it say? Part C. According to what does it say? According to the model, will the medicine ever disappear from the body? Comment on the difference between theoretical math and real life. Remember, this is a exponential function. So I'm starting with 1,000. I'm going to get half, 75%, then 75%, then 75%, then 75%. It's going to turn into an exponential function, as you might imagine. And it's going to get closer and closer to the value of 0. According to our math, is it ever going to hit 0? Does an exponential function ever touch 0?
No.
No, it doesn't. Does that mean you take Tylenol, it's going to be inside your body for the rest of your life? Can you comment on theoretical math versus reality? Yep, I can do that, Monad. Give me a second. So if this is my equation, digestion works differently. Everything actually works a little differently. According to our math, it will never hit 0. But in real life, your body will be able to get to the very last little bit of the drug and get rid of it. So to comment on theoretical math versus real life, theoretical math will help us given a time frame that we find useful. After a certain point, it won't model real life properly. So this is also the reason why we might have to specify domain and range. We specify domain to show how far are we able to use the math to mimic real life, and then after that point, everything sort of falls through the ground. It falls through the cracks. It just, it doesn't work. So it's all sort of coming together. I hope you get a sense of this. Okay, I'm going to go ahead and answer Monad's question of how to do this in the calculator. Everyone else, my request, can you try questions 4, 6, and 7 on your own? Do your best in identifying A, the base value, the time exponent, the n, and maybe even the y value if they give it to you, the final value. See if you can apply that into your function and see if you get the final answer. I believe the final answer, I'll write it down the final answer. You can compare it in just a second. Monad, give me a sec. Give me a sec. Question 4, answer is, let's see, 8. 1, 2, 9, 1,000, 16,000, 871 people. Is that right? So that's as a thing, yes. Okay. Part B. Part B. Q6. All right, so these are 3 questions, 3 answers. See if you can match them. If you find some difficulty, if you're not quite sure why or whatnot, I am going to address it and answer it for you. That's all I have for you today, and the rest is for you to just continue to practice for our test. I think it would be 16.872 because it is a zero point 0.5 and it was rounded up before. You're right. I could argue the same way. It's very similar. I think you get like 88,129 point something zombies, which means that human is on his way to be a zombie. So I don't know. We'll figure it out. Monad, if you're with me, here it is. On your calculator, let's take a look. 5,000, so 5,000, 1.10 to the power of 25. Okay, I don't know what that small difference meant on the... No, Ian, absolutely not. I am testing you to see if you know how to work that math. Monad, I'm not sure what calculator you have. Yes or no? Do you have this button or do you have this button? What kind of button do you have on your calculator? I don't think you're chatting. Okay, I'm not sure if it's because I'm hearing this, but here's what one type of calculator you'd have to do this. You would have to do 1.10. You would press the YX, okay, and then you type 25, and then you do the equal sign. Whatever you get as your answer, you just multiply by 5,000, and then you should get your final answer. Some calculators, like if it's a computer style calculator, you might have to do this in reverse. You might have to write 25 first, which is a little weird, I know. But you write 25, and you say 25 is the exponent of 1.10, and then you press the equal sign. And then that answer, you then multiply by 5,000. It really depends. Sure. You know what? Oh, I can't. Oh, wait. You open the camera? Let me see. Okay, give me a sec. I gotta open you up. I gotta make you bigger because I can't see otherwise. Uh, Pin. Let's see. It's so small. Can you raise your calculator a little bit? Bring it up. Wanna bring your calculator up a little bit? Okay, yeah, on the left. Left second button is a YX. You have one of these. Yep, that one. Can you press 1.10 and then YX and then 25? What do you get? Yes, perfect. Yeah. You press equals. Yep, and then from here, take that answer, the answer, multiply by 5,000. Equals. Yep. Yep, that's $54,173.53. Good. That's it. So for you, you have a regular scientific programming calculator, which is great, which is fine. See if you can apply that for all of these other questions. Oops. No worries, no problem. Glad to help. Can you back to 3B for a second? 3B. I sort of erased it. but I will rewrite it. For 3b, yeah. Oof, while you're working, watch out, people. You might want to put me on mute. My daughter's starting to throw a fuss. So you might hear a crying baby, which is not the happiest sound out there. Really annoying. No worries. Glad to help. I'm gonna give another 5 minutes, and then I'll begin to take questions. If you got numbers 4, number 6, number 7, I'm literally gonna set you free and dismiss you because you can use this extra 20 minutes to either take a break or start organizing your notes to better prepare for the test. Okay, so if you do decide to leave on me, here's a couple of things you can do. Organize notes, okay, and make a list of questions. Yep, I can do that. List of questions um, for sections, for whatever sections you found to be most difficult throughout our journey so far. Make a list of it and focus on those because the other ones I'm hoping you have confidence on. Number two, I already talked to you about the test and what you can expect, so I'm not going to talk more about that. Chapter 1 is basically full of grade 10 stuff. It's like a mixed bag of all these different techniques like partial factoring, quadratic formula, um, completing the square, and all that kind of stuff. So maybe you want to, devote a good chunk of your time to chapter 1 because chapter 2 and 3, as you can see, has a lot to do with transformations, plus certain miscellaneous things in chapter 2 and some miscellaneous things in chapter 3, like these word questions, right? So take your time with it. Also, start making your study sheet that you know you're allowed to have. Just, yeah, make sure you got it, right? And make sure you bring it and you know how to use it. You don't want to waste time looking at a study sheet and trying to figure out what you wrote there. Okay. I am going to go through question 4. Um, yeah. So any questions before I start question 4? Okay. So let's go through question 4. If you feel like you're getting the hang of it and you want to step out, I totally get it. Not a problem. I'm going to move on and try this question. You have a different answer for question 4B. Can you explain it? Okay. I figured as much because there's a whole bunch of numbers you have to pull out the correct ones. So take a look. It talks about 25,000 humans, okay? And it also talks about a single zombie being created, right? Some people are like, oh, it's 25,000. That's going to be my A value. That's not true. Let's continue reading the question. I have one zombie with a growth rate of 35%. And how much time passes? 30 minutes. Which works because this is also in minutes. Your equation should be one zombie growing by 35% per minute, and it happens, sorry, this is not time. Oh yeah, it is time. It happens for 30 minutes this growth happens every 1 minute, so I don't have to write that. This should be your actual equation. Some of you might have written 25,000, 1.35. That's not true. Why? This is talking about the growth of zombies. This is talking about the amount of humans left over. Is this the starting value of all the zombies? No. This is the starting value of the humans. Some people might have also written, okay, if I'm growing by 35%, maybe I am decreasing by 35%. That's also not true, because the growth rate of a zombie of 35% is not equal to the same percent of 25,000. Your final answer, if you do 1.35 to the power of 30, should bring you to 8,129. That means out of 25,000, 8,129 people became zombies, leaving me 16,871 people still alive. I have a question saying, why is it +1 for the b value? Remember, the growth rate, if you're given a percentage, is always the original 100% plus whatever percent we're growing by. So in that way, it's always going to be 1.00 plus, so in this case, if it's 35%, so I'm essentially multiplying by 135% of the original, right? I am multiplying the value by 1.35 every single step of the way. And that's not really some kind of formula or anything like that. It's just, I have the original, I'm growing on top of the original, so by logic, it has to be 135% from previously. So 1.35.
So the 1 was added to the 0.35 as like the initial zombie, like the first zombie, right?
Yes.
Okay.
So the original right now is 1 zombie. I'm adding an extra 35% of that. So in other words, after 1 minute, there is 1.35 zombies, which I know doesn't make sense, but for the sake of the question, that does increase slowly. The 1 always is there, because we have to talk about the original. Great. Yeah, this is good. Yeah, this is why I'm saying, like, I feel like exponential functions can have more creative, more fun questions. I can't wait until we get to the final chapter, chapter 7, so that we can start talking about exponential functions in terms of money. And we're going to investigate how that could play with you, how you can make math work for you literally in terms of money. And we'll investigate some interesting questions like, what do you have to do now for it to exponentially grow and you can retire comfortably? Because frankly speaking, you, as my students, have something I will never have ever again. What is that? Time. You have like probably, you guys are 17 this year, so you have almost like 20 years on me. I mean, I have 20 years on you. You have 20 extra years to let that money grow. So if you act now, you'll be richer than I will ever be. So take that to the bank. I got another question asking to do part B. That's totally cool. All right. So now we're working into a different scenario. So this amount of people they start to see the amount of zombies, and they're like, oh, we gotta hide. So the growth rate is not 35% anymore. Take a look at the question. It says the growth rate drops to 1%. So now the growth rate is this. How many zombies are we starting with if this is the growth rate of the zombies? 30 minutes have passed, so the growth rate is applied to that many zombies. Okay? So it's not like these zombies turn into one. It's not one anymore, right? You still have 8,000 zombies walking around. But because people are hiding, the growth rate is very slow. Next. Time is also a trick. It says how many zombies are left, or how many people are alive after 2 hours from the first bite. So you think, oh, 2 hours, that's going to be 120 minutes because we're doing this in minutes as well. But careful, the question says 2 hours since the first bite, so the first victim. So go back to the original question. How many minutes passed so far? 30. That means if 2 hours passed in total, then 90 more minutes have passed at this new growth rate. So that's a little bit of a trick from the story, not the math, just the story, right? If it's 2 hours since the first victim, 30 minutes passed, that means another 90 minutes must have passed. So my total number of zombies based on time is 8,129. My growth rate is now very low, but that happened for another 90 minutes. That brings us to approximately 19,900 and about 5 zombies. So how many people are alive? You subtract 25,000 with 19,905. You have about 5,095 people still alive. Everyone's like, well, that's what happens in the movies, right? Right? What's going on? And this used to be this kind of question was really popular with the students back when, like I think 10 years ago, there was a huge wave of zombie movies. Even like 20 years ago, like 28 Days Later, 28 weeks later, um, World War Z, all that stuff. And if you haven't seen it, I think I keep on recommending. This is a Korean video that you find on Netflix with subtitles. Train to Busan is a little scary, but if you like that stuff, go for it. It's really good. It's scary, but it's really good. Those Korean actors, man, they know how to act like zombies. They're really good. In that movie, are they in apartments? Honestly, no, I don't think so. The entire movie occurs on a train. Noah, I believe all of chapter 3.6 are word questions, so you can take a look at that. Wouldn't it be subtracting from the A value of people remaining? Oh, I get what you're saying, but this actually accounts for it. See, the zombies grew to this much. So the zombies that were already created, now this is the new number of zombies, which means it's still subtracting from the total of this. No, there's a lot of zombie movies out there. Uh, no, think carefully about it. Think about it. Um, if I was doing a full 120 minutes, my starting zombie would have been 1, and my growth rate would have been somewhere in between 35% and 1%. Right? If we're doing a full 120 minutes, the zombie started with 1 back then. And so just we're basically turning it into two different scenarios, right? If this is a timeline, from 0 and 120 minutes. From 0 to 30 minutes, we have a base of 1.35, right? And it lasts for 30 minutes, and 1 grew to 8129. From 30 to 120, which is a time factor of 90 minutes, the base is 1.01. You could think about it like that. Two different scenarios completely. Okay, well that's actually there's good questions, and I'm glad people were on board, which tells me all my other lessons were really boring, which is probably true. It is 3:10. If you would like to take off, you are informally dismissed. I got 5 more minutes with you, and I'll stick around to answer any questions you have. What's the answer to 6? Answer to 6 is 10.1 billion. So it's approximately 10.135 million, approximately. Bye, Ellen. Bye, Monad. Work hard. Keep working on that calculator. Forgetting how to work scientifically, but I got 1.0. That is correct. It is correct. So 10 point. So million is 0.00000. What your calculator is doing is taking the decimal that should be at the end of the number, bringing it up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times, giving you a value of 1.01, and then saying you moved it up 10 times. So it is correct.
Mr. Kim, could you quickly run through question 6, if that's okay?
Question 6. Yeah, absolutely. So again, this is the population thing. Many years ago, my starting value of the population is 4.5 billion. But the question, for some reason, asks you to answer in millions. So I'm just going to turn it into millions. The growth rate is 2%, which means the base that I use is 1 plus r, which is 1.02. How much time has passed? Oh, sorry. And also, the rate is based on per year, so the end value is 1. The time is, right now is 2021. The 4.5 billion was 1980, so the amount of years that passed is 41 years. So using this template as my equation, time over n, the population when 41 years has passed is 4,500 million, my growth rate of 1.02, and 41 years every 1 year is when I multiply, so I even have to write that. You should be getting 10.135.
Okay, perfect. Thank you. I just wasn't sure how to get the t value.
Got it.
All right, thank you. Have a good afternoon.
Yep, you too. Okay, bye everyone. All right, it's 3:15 basically. Anyone else? Clara, do you have a question, or Noah? Okay, then at this point, I'm gonna close so that I can put up this recording for other people who might want another breakdown of this. Okay, I'm going to Oh, you said you were posting review sheets tomorrow, right? No, actually, the review for chapters 1 to 3 is already online. I've already put up answer key as well, so you can take a look at that. I think the review sheet you might have taken already last time you were in class because I did provide a hard copy of it. Okay, give it a shot, and I will see you next time.